February 1942. North Atlantic. The ocean is dark, heavy, and indifferent. A Liberty ship cuts through the swells, its engines pushing against wind and fear. The convoy around it feels smaller every night. Radar is still unreliable, escorts are too few, and the U-boats hunt with a precision that seems almost surgical. Then, without warning, a column of water erupts beside the freighter. One torpedo. One hit. Within minutes, the ship lists, burning oil spreading across the waves. Sailors climb the rails, trying to escape the heat that crawls across the surface like a living thing. Some jump into the freezing water, knowing they may not survive the cold long enough to be rescued. Scenes like this unfold almost daily. By the spring of 1942, German submarines are sinking Allied ships faster than the United States can build them. Factories in New Jersey, California, and Louisiana run day and night, but the math refuses to cooperate. Every time a new convoy forms, another graveyard of steel rises from the seabed. In Washington and London, the panic is quiet but real. Military briefings speak of tonnage deficits and shipping attrition curves, but behind those phrases lies a simple truth. If this trend continues, Britain starves. And if Britain starves, the United States fights alone. It is in this atmosphere, this tightening vice of numbers and desperation, that impossible ideas begin to feel reasonable. Commanders ask for more escort carriers, but they take years to build. More destroyers, but steel is rationed and shipyards are overloaded. More long-range patrol aircraft, but the distances are too vast and the bases too few. The enemy's advantage is mobility. The Allies need something that can stay at sea for months, survive torpedoes, and carry enough aircraft to push the U-boats out of the Atlantic. And in 1942, such a vessel simply does not exist. But in Ottawa and Washington, a small circle of planners begins to wonder. If the limits come from steel, what happens if the answer isn't steel at all? What if a new kind of material, cheap, abundant, and strangely resilient, could create a ship so large and so durable that no torpedo could sink it? A floating fortress capable of crossing oceans without refueling, immune to fire, and long enough to launch bombers. A ship that would not be built, but grown. An idea that sounds absurd, until the numbers demand it. This is the moment when American engineers first hear a strange name whispered through interdepartmental cables: Habbakuk. A proposal so unconventional that it bypasses traditional naval architecture entirely. A proposal born not from imagination, but from necessity. In a war where steel is scarce and lives are measured in tonnage, the United States is about to consider something that seems to defy both physics and common sense: a supercarrier made of ice. And in the months ahead, that fragile, impossible material will capture the attention of generals, scientists, and a few visionaries who believe that survival sometimes requires stepping outside reality. The Atlantic is bleeding. And somewhere in that cold arithmetic, Habbakuk begins to take shape. The idea first surfaces in a modest research memo passed quietly between British and American liaisons in 1942. The document is thin, typed hastily, and almost unbelievable in its claims. It speaks of a new material, simple, inexpensive, and strangely strong. A composite made from two ingredients so ordinary that engineers on both sides of the Atlantic read the report twice to be sure they hadn't misunderstood. Ice and wood pulp. The mixture has a name: pykrete, coined from the British inventor Geoffrey Pike, a man whose imagination often outpaced the technology of his age. Pike was eccentric, unpredictable, and brilliant in a way the war sometimes needed. He believed that conventional thinking was a luxury the Allies could no longer afford. According to the tests, pykrete was nothing like regular ice. When frozen under controlled conditions, its fibers formed a network that limited cracks, absorbed impacts, and resisted shattering even when struck with great force. A bullet fired at close range left only a shallow crater. A torpedo, theoretically, would cause damage, but not catastrophic failure. For American engineers accustomed to steel, the idea bordered on madness. Ice melts. Ice cracks. Ice flows under pressure. But the early British experiments presented a different story. A block of pykrete remained solid for hours at room temperature. When submerged, It resisted erosion better than expected. And most importantly, producing it required little more than water, wood, and cold, resources the Allies had in abundance in northern Canada. Still, the United States needed proof. That proof arrived indirectly, in the form of one of the strangest demonstrations ever staged in wartime science. A British officer, confident in the material's durability, placed a block of pykrete on the floor during a meeting. To the surprise of those present, he drew a pistol and fired into it. The bullet ricocheted, slicing across the room and embedding itself in a wall. The message was clear: this was not ice as they understood it. Word of the demonstration spread quickly through scientific channels. American naval architects, chemists, and materials specialists examined the data, searching for weaknesses. They found plenty: temperature sensitivity, creep deformation, unpredictable fractures, but they also found possibilities. For the first time, the idea of a floating platform made not from steel, but from a frozen composite, felt technically interesting rather than absurd. The biggest question was not whether pykrete was strong enough. It was whether it could be controlled. To turn it into a 2,000-foot vessel, the United States would need refrigeration systems running continuously inside the hull. They would need temperature-regulated construction sites, insulated bulkheads, and an understanding of how the material behaved over months, not days. They would need to model stresses no engineer had calculated before. But above all, they would need to decide whether the strategic situation justified the risk. Could a material born in a laboratory, and backed by desperation, become the backbone of a new Atlantic strategy? By mid-1942, American planners were leaning toward yes. The shipping crisis was worsening. Escort carriers were still too few. And a vessel made from pykrete, if it worked, could patrol wide sections of the ocean for weeks at a time. The idea was no longer a curiosity. It was becoming a candidate. As one U.S. Navy analyst wrote in a private note, "We are running out of steel faster than we are running out of imagination." And imagination, in the summer of 1942, was beginning to feel like a weapon. By late 1942, the United States and Britain were no longer discussing whether pykrete worked. They were discussing what could be built with it. And the design that emerged from these early conversations was nothing short of audacious. A ship, if ship was even the right word, so large that no existing naval yard could have contained it. A vessel whose dimensions dwarfed every carrier afloat, not by meters but by magnitudes. The preliminary estimates spoke of a hull nearly 2,000 feet long, wider than a battleship is tall, and weighing more than an entire fleet combined. It would not be launched in the traditional sense. It would simply exist, constructed in a frozen lake, grown layer by layer, winter after winter. Engineers on both sides of the Atlantic tried to visualize it. A floating platform the length of Manhattan blocks. A deck spacious enough to host long-range bombers. Storage bays capable of holding thousands of tons of fuel, ammunition, and supplies. But at its heart, the ship's defining characteristic was something no navy had ever considered. It wouldn't need armor. Torpedoes could gouge it, but they couldn't sink it. Its mass alone made it almost unsinkable. Still, ambition required details. And this is where the United States stepped in with the weight of its industrial expertise. American refrigeration specialists proposed embedding a network of cooling pipes throughout the hull, miles of tubing that would circulate cold brine, keeping the structure stable even in warmer waters. Naval architects suggested a skin of insulating material, a kind of artificial rind, to protect the pykrete from sunlight and spray. Structural experts debated the ideal wood-pulp ratio, the optimal freezing rate, the thickness of the outer shell. On paper, the ship began to make sense. Not elegant, not beautiful but possible. It would travel slowly, barely 7 knots, but speed wasn't its purpose. Its mission was endurance. To remain at sea for months, functioning as a floating airbase in the mid-Atlantic, projecting power into the vast empty spaces where U-boats hunted. With long-range aircraft stationed aboard, convoys could be shielded from above in areas once considered unreachable. But the moment that truly galvanized American interest came when a small group of naval analysts performed a terrifying calculation. If the shipping losses continued at their 1942 rate, the Allies would face a catastrophic collapse of transport capacity by early 1943. A collapse that no number of Liberty ships could compensate for. The United States didn't just need more ships. It needed a new category of ship, one that could be built without consuming steel, copper, aluminum, or any of the materials already stretched to their limits. Pykrete suddenly looked less like a curiosity and more like a strategic loophole. And so the question shifted from, could this work, to, how fast can we make it real? For that, they needed a place cold enough, remote enough, and vast enough to host a prototype. A place where construction could begin immediately, without drawing attention. A place where an entire naval concept could be tested before winter ended. They needed Canada. And Canada was ready. In the winter of 1942, American and Canadian engineers converged on Lake Patricia, deep in the wilderness of Alberta, to create something the world had never seen, a frozen prototype of a warship that might reshape the Atlantic. It would not be pretty. It would not be smooth. But it would be the first step toward a vessel built not from steel, but from cold ambition. Winter settles over Alberta with a weight that feels almost geological. The forests surrounding Lake Patricia freeze into silence, the snow absorbing every sound except the distant hum of generators brought in by the engineering teams. It is here, far from shipyards, far from steel, that American and Canadian crews prepare to build the first full-scale demonstration of what a pykrete ship could be. The prototype is modest compared to the vision, a rectangular block, roughly 60 feet long, kept frozen not by nature alone but by a network of pipes and a diesel-powered refrigeration system tucked inside like a mechanical heart. Yet to the engineers gathered around the site, it is more than a frozen rectangle. It is proof of concept, something tangible they can measure, test, and, with luck, improve. Construction is nothing like traditional naval work. There are no rivets, no plates, no scaffolds rising from drydock floors. Instead, teams spray layers of water mixed with wood pulp, letting each coat freeze before adding the next. The process is laborious, cold, and strangely quiet. The structure grows slowly, almost organically, like a glacier being coaxed into shape. Within days, a problem emerges, one they expected but underestimated. Ice does not stay still. It creeps. It shifts under its own weight. It strains against supports that seem rigid to the human eye but meaningless to the physics of frozen composites. Cracks appear where no cracks should be. Edges warp. Corners bow outward, as if the material were reminding its creators that nature is always a partner, never a captive. The refrigeration system helps, but it does not solve everything. Inside the prototype, temperatures fluctuate. In some pockets, the pykrete remains firm and dense. In others, it softens, sweating under the influence of ambient heat. Engineers crawl through narrow maintenance channels, taking notes with pencils that barely write in the cold, documenting stresses and deformation curves that textbooks do not yet contain. And then there is the noise. As the structure responds to wind and temperature shifts, it emits low, unsettling groans, natural, harmless, but impossible to ignore. To some of the workers, the sounds resemble a ship talking in its sleep. To others, they are a reminder that the material is alive in a way steel never is. Despite the challenges, the prototype holds. It floats. It resists damage far better than expected. And most importantly, it does not deteriorate, even after weeks exposed to sunlight and surface-level stress. Word of the results reaches Washington swiftly. Reports emphasize both the promise and the problems, the need for stronger refrigeration, improved insulation, and a deeper understanding of how pykrete behaves under prolonged strain. But the fundamental conclusion surprises everyone involved. The idea works. Not perfectly, but undeniably. Encouraged, planners begin drafting the specifications for a full-scale vessel. They imagine hangars, workshops, elevators, fuel storage, and living quarters embedded within a frozen hull thicker than the walls of a fortress. They debate how to anchor engines to a material that can slowly deform. They design internal steel skeletons meant not to replace the ice, but to guide it. Yet for every solution, new obstacles arise. Weight distribution, thermal gradients, cost. construction time, crew safety, and the quiet, unspoken concern. What happens if the refrigeration systems fail in the middle of the Atlantic? The prototype on Lake Patricia cannot answer that question, but it can answer another. Habbakuk is no longer science fiction. It is engineering with a pulse. The ice holds. For now. By early 1943, the technical reports from Lake Patricia land on the desks of senior officials in Washington. They come bundled with photographs, thermal charts, stress diagrams, and a summary that is both encouraging and alarming. The prototype works, but it works on its own terms. Pykrete behaves like a living material, resilient when cold, stubborn when stressed, unpredictable when temperatures drift even slightly. The reactions inside the U.S. Navy are split almost perfectly in half. On one side stand the visionaries, engineers, analysts, and a handful of officers who believe Habbakuk could break the bottleneck strangling Allied shipping. They argue that the project offers something no conventional ship can match: size without steel, durability without armor, and endurance without fuel-hungry escorts. They imagine an unsinkable airbase roaming the mid-Atlantic, its deck crowded with long-range patrol aircraft, Catalinas, Liberators, Avengers, hunting submarines across territory once controlled entirely by the enemy. On the other side stand the realists, men with decades of experience in shipbuilding and naval operations. They raise questions the material supporters struggle to answer. How will the refrigeration system be maintained at sea? How will the hull react under storm-level stress? What happens if a torpedo ruptures a cooling line deep inside the structure? And most pressing of all, how do you crew a ship made of a substance that melts? The United States is already stretched thin. Every new idea demands steel, labor, logistics, and political capital. A Habbakuk-class vessel would consume tens of thousands of tons of wood pulp, millions of gallons of water, and an isolated construction zone the size of a county. It would require engineers familiar with a material that behaves unlike anything taught in naval academies. And it would demand a multi-year commitment at a time when victory still feels fragile. Meetings grow tense. Some officers dismiss the project as a distraction built on winter. Others see it as the only way to outpace the relentless efficiency of German submarine warfare. Reports circulate predicting that a full-scale Habbakuk could cost more than the largest steel carrier ever built, despite requiring no steel itself. The irony is not lost on anyone. Amid the debate, the broader strategic picture begins to shift. New technologies, longer-range aircraft, improved radar, refined depth charges, and escort carriers rolling off American production lines start to tilt the balance in the Atlantic. Shipping losses fall for the first time since the war began. Convoys become safer. U-boats become hunters turned hunted. The question quietly changes from, do we need Habbakuk? To, do we still need Habbakuk? Still, the idea refuses to die. Its supporters remind decision-makers that victory is never guaranteed, and innovation often looks absurd before it becomes inevitable. They insist that a single massive pykrete vessel could patrol supply lines stretching from Nova Scotia to Scotland, exerting pressure on enemy submarines in places aircraft cannot reach regularly. But for the first time, cost-benefit charts begin to overshadow imagination. Engineers calculate the power needed to keep a multi-million-ton block of reinforced ice frozen through the Atlantic summer. The numbers are brutal. Refrigeration alone would require generators the size of small factories. The hull's thermal insulation would need constant maintenance. Even minor temperature fluctuations could warp internal structures and compromise flight operations. And then comes the logistical bombshell. Constructing a full-scale Habbakuk would take at least 2 years, maybe 3. In 1943, that is an eternity. As these realities settle into the minds of planners, enthusiasm cools. The project that once seemed like a bold escape from strategic desperation now begins to feel like a relic of a darker time, a solution for a crisis that is slowly, steadily being solved by other means. Still, no one is ready to abandon it. Not yet. A final round of assessments is ordered. Technical teams expand their tests. And a quiet sense of doubt begins to mingle with the cold ambition that fueled the idea from the start. Habbakuk is alive. But it is breathing slower. Spring 1943 arrives with a quiet shift in the war's momentum. The North Atlantic, once a graveyard for Allied shipping, begins to stabilize. Long-range aircraft from Greenland, Newfoundland, and Iceland close many of the air gaps that once protected German submarines. Escort carriers, small, fast to build, and increasingly effective, join convoy after convoy. And improved sonar and radar give Allied ships a new advantage in the underwater duel. Inside the Pentagon, these developments begin to erode the urgency that once made Habbakuk seem indispensable. But the project is still alive, and it still needs answers. A new technical committee is formed, bringing together American naval architects, refrigeration experts, physicists, and military planners. Their goal is simple and brutal: calculate exactly what a full-scale Habbakuk would require. No optimism. No shortcuts. Just numbers. Those numbers arrive in a stack of documents thicker than a pilot's manual. The first shock concerns size. To support aircraft operations, the ship would need a deck nearly 2,000 feet long enough for fully loaded bombers to take off safely. But a deck of that size creates structural stress beyond anything ever attempted with frozen materials. Even with internal steel reinforcement, the pykrete would deform constantly. The refrigeration system would need to fight not only melting, but creep, ice slowly flowing under its own weight. Then comes the refrigeration load itself. Cooling a structure of this magnitude is not a matter of a few diesel generators humming beneath the surface. The calculations show that the ship would require dozens of industrial-grade refrigeration plants running continuously, consuming fuel at a rate equal to, or even exceeding, that of a conventional carrier. And if any section of the cooling grid failed for more than a few hours, entire compartments of the hull could weaken. Engineers also raised doubts about repairability. How do you fix cracks in the hull during a storm? How do you replace cooling pipes embedded deep inside a frozen wall? How do you guarantee the safety of a crew living inside a structure that behaves more like permafrost than metal? The British side proposes new insulation layers, while American teams explore the idea of hybridizing the hull with internal steel trusses. But each proposed fix adds weight, complexity, and cost. A project born from the promise of cheap and simple begins to look neither cheap nor simple. Then comes the most devastating report: the construction timeline. Even with a massive workforce and access to northern lakes large enough to serve as natural shipyards, the vessel could not be completed before late 1945, at best. And that timeline assumes ideal conditions, perfect winters, and a stable supply chain of wood pulp and equipment at a moment when every resource is already strained. A senior naval analyst summarizes the problem in a single sentence that circulates in memos across Washington. Habbakuk will not save the Atlantic in time because the Atlantic is already being saved. It is a quiet admission, but a decisive one. The crisis that birthed Habbakuk is evaporating. U-boats are dying faster than they can be replaced. American shipyards are producing steel vessels at unprecedented speed. The war is shifting from survival to superiority. And in that new reality, a ship of ice, impressive, imaginative, and technically fascinating, begins to look like a monument to a past emergency, not a tool for the future. Still, no final decision is made. Not yet. The project remains on the table, held up by a mixture of scientific curiosity, political caution, and the stubborn hope that innovation might reveal a breakthrough at the last moment. But the ice is thinning, metaphorically and literally. The question is no longer, can we build it? It is, should we? And in Washington, that answer is about to become unavoidable. By the summer of 1943, the atmosphere surrounding Habbakuk has changed. What was once a bold, almost desperate leap into uncharted engineering now feels like a question hanging in midair, important, intriguing, but no longer urgent. And urgency is the oxygen of wartime innovation. Without it, even the most daring ideas begin to fade. The decisive moment comes during a series of joint meetings between American and British officials in Washington and Quebec. The participants range from naval planners to refrigeration engineers, from strategic analysts to senior officers who have watched the Atlantic War evolve day by day. Habbakuk has always lived in the space between imagination and necessity, but now it must face the cold arithmetic of progress. The British delegation presents updated projections first. Their numbers are thorough, their diagrams precise, but the story they tell is the same one American engineers have already seen. Creeping costs, rising complexity, and a timeline that drifts further into the future with each revision. The refrigeration requirements alone, they note, would consume a staggering amount of fuel that could be used to power dozens of escorts or aircraft instead. When the American team steps forward, the room grows quiet. Their analysis is blunt, even painful. They acknowledge the innovation behind pykrete. They recognize the ingenuity of the Lake Patricia tests. But they also lay out the reality. The war is changing faster than the project can adapt. Long-range B-24s are patrolling areas previously unreachable. Escort carriers are becoming the workhorses of the convoy system. Hedgehog mortars, improved sonar, and new radar variants are turning submarine hunting into a science. And U-boat losses are mounting at a rate the Kriegsmarine cannot sustain. One American admiral says what everyone else is thinking. We are solving the problem with tools we already know how to build. Silence follows. Not defiance, just the sinking recognition that the logic is sound. There are still passionate defenders in the room. Some argue that Habbakuk could serve the Pacific in the post-war era. Others insist that abandoning it would waste the breakthroughs made in composite, ice, and battlefield refrigeration. But even they cannot deny the central truth. The project was born for a crisis that is no longer killing convoys the way it once did. The final blow comes not from the engineers, but from the accountants. Their report projects that a full-scale Habbakuk would cost more than building multiple fleet carriers, despite being made of ice. Between refrigeration plants, internal steel framing, insulation, and specialized equipment that does not yet exist, the financial logic collapses. By the end of the meeting, the tone has shifted from debate to acceptance. Habbakuk is not cancelled with a dramatic announcement. There is no single order, no ceremonial end. It simply becomes clear, to everyone in the room, that the project will not proceed. Still, no one leaves satisfied. Because behind all the calculations lies a quieter, more human truth. This was an idea that pushed boundaries. An idea that asked nations to rethink the materials of war. An idea that thrived in the thin air between desperation and ingenuity. And now, like ice exposed to sunlight, it is beginning to melt. As the meeting adjourns, folders are closed, diagrams are rolled up, and the future of naval warfare quietly shifts back towards steel, engines, and the technologies that can be built quickly and reliably. Habbakuk is not dead. But it is no longer alive in the way a weapon must be. It becomes something else entirely, a remarkable technical detour in the story of a global war. One that will be remembered not for failure, but for daring to ask a question no navy had asked before. What if the future wasn't forged, but frozen? When the final reports are filed and the committees disband, Habbakuk does not vanish. It lingers, half legend, half engineering experiment, embedded in the memories of those who saw its potential. The prototype on Lake Patricia remains frozen through winter, slowly sagging as spring returns, its once straight walls softening under the sun. By summer, the structure begins to lose its shape. By autumn, it is gone, reclaimed by the quiet lake that held it. But the idea does not disappear with it. For the engineers who worked on the project, Habbakuk becomes a reminder that innovation often comes not from confidence, but from pressure. At a moment when the Atlantic War was slipping out of control, the United States and Britain dared to consider a solution that ignored every established rule of naval construction. They explored a material no naval architect had studied, tested structures no textbook described, and calculated stress loads for a substance that behaved more like geology than metallurgy. And in those months of exploration, they expanded the boundaries of what wartime engineering could be. Even the project's failure carries its own value. The refrigeration studies developed for Habbakuk influence future research on Arctic bases and cold weather logistics. The pykrete experiments inform composite research long after the war ends. And the interdisciplinary cooperation, naval architects, physicists, chemists, designers, sets a precedent for the kind of integrated problem-solving that later defines the Cold War era. For the military strategists of 1943, the end of Habbakuk marks something else, a shift in mindset. The war is no longer about surviving an onslaught. It is about shaping the endgame. With the Atlantic secured, the United States can focus on the Pacific, on Europe, on the complex orchestration required to push the Axis back on every front. The idea of a massive frozen aircraft carrier becomes a chapter of a past crisis, a crisis that has already begun to fade. Yet history often preserves the unconventional better than the familiar. Steel ships are built, used, retired, and forgotten. But a ship made of ice, one that almost existed, one that almost shaped a theater of war, lives on as a symbol of a particular moment in human history, the moment when imagination collided with necessity. In hindsight, Habbakuk reads like a parable about the extremes of wartime innovation. It teaches that some ideas are valuable not because they succeed, but because they force us to look at the problem differently. It shows how fear, creativity, and science can combine into something wildly improbable and deeply instructive. And it reminds us that wars are not won only by the technologies that enter combat. They are also shaped by the experiments that never leave the drawing board, by the prototypes that melt in the sun, by the paths abandoned because the world changed faster than the engineers could build. Standing on the shore of Lake Patricia today, you won't find a trace of Habbakuk. No steel, no wood, no machinery, only water, cold, clear, silent. But beneath that surface once lay the outline of a dream, a floating fortress of ice, conceived in desperation, tested with conviction, defeated not by enemy action but by the steady momentum of a war turning in the Allies' favor. In the end, Habbakuk was never launched. But it proved something just as important, that in moments of crisis, the limits of possibility are far wider than they appear. And sometimes, the most extraordinary weapon of all is the one we choose not to build.